Hello and welcome in a new video. We will introduce now the notion of absolute motion, relative motion, driving motion. So we will introduce what happens in the case of the change of reference frame. So let's take an example. Here we have a moving track. It's moving to the right, and we have a child who is throwing a ball upwards. Okay, now we will study the motion of the ball as seen by the child. So the child will see the ball going up and then down in a vertical line. So we are studying the motion of the ball with respect to the child, or with respect to the frame of reference related to that. So the truck moves with a constant velocity to the right, and the observer in the truck here, which is the child, is throwing the ball straight up. So for the child or for any observer on the truck, he will see the ball going up and down in a vertical path. So here we are considering the reference frame related to the truck or to the observer in the truck. So let's consider OXY like this. What happens if now the same object now is being observed by another observer on the ground? Would the observer at the ground see a vertical path or a different path? Okay, now we have another observer on the ground, a stationary observer who is not moving. We have the same child throwing the ball upwards, and we have the same truck moving to the right. Okay, for this observer, or if we draw the frame of reference related to this observer, noted as OX1, Y1. So for this observer on the ground, this observer will see first the ball moving upward, and also this observer on the ground would see the ball moving to the right, because the ball is thrown by the child who is moving with the moving truck. So the observer on the ground will see that the ball will have two directions. It will have a motion upwards because the ball is being thrown upward, but also the ball will move to the right at the same time. Okay, and this, so we have here Vy and Vx, so the ball will move in this direction, and the ball will follow a parabolic path as seen by the observer on the ground. So the motion of any object depends on who is observing this motion. Is this motion being observed by a stationary observer or by a moving observer? Okay, so for this observer at rest, he will see the ball following a parabolic path upward and to the right at the same time. But for the observer on the truck, this observer will see the ball going up and down, so following a vertical path. So here we can see that by changing the reference frame, we have different types of motion. Okay, so here we can distinguish between absolute motion, relative motion, and driving motion. Okay, if let's check this motion. Okay, so for the observer on the ground, the ball will go upward, and also to the right, so that we can see that the velocity of the ball can be written as following. So V absolute, it means that the velocity of the ball with respect to a stationary observer, so we say that this is V absolute. The absolute motion is being observed by a stationary observer, or it's seen by an observer at rest. This velocity is a combination of two velocities. One velocity is the right, Vd, and another velocity which is vertical, and this is Vr. So what is Vd? Vd is the motion of the truck, it's the velocity of the truck to the right, and Vr, it's the velocity of the ball, but as seen by the moving observer. Okay, we will see this relationship later on, but I want you to understand that the absolute velocity, it's the velocity as seen by an observer at rest, and it can be the composition of two velocities. So Vd is here, it's the velocity of the truck or the velocity of the moving frame, plus Vr, it's the velocity of the object as seen by the moving observer. So we can distinguish the absolute motion, which is the motion observed by an observer at rest. So it's the motion observed by this observer, this stationary observer, or this observer which is not moving. We can distinguish the relative motion. It's the motion observed by a moving observer. So here, the child here who is moving with a moving truck is seeing the relative motion. And we can talk also about the driving motion, which is the motion of the moving frame. It's the motion of the moving truck here. Okay, because while it's moving, everything moves with it. Here, while the truck is moving, also the child is moving, the ball is also moving, and everything in the truck is following the motion of the truck. So this is what we call the driving motion. While the truck is moving, it drives everything with it. Let's consider this frame at rest. So we have O1, X1, Y1, Z1, a frame which is at rest, it's not moving. We can say that this is a stationary frame. We can say that this is a frame at rest. Okay, and we have an observer at O1. So O1 is the origin of this frame, and we have an observer at O1. The base for this frame is I1, J1, and K1. We say that this is the fixed frame, or a frame at rest, or a stationary frame. And we have also another frame. This is the moving frame. For example, let's say this is the frame of the related to the truck, for example. This frame can move, it can make a translation, it can make a rotation. And so this frame is represented by OXYZ and by the base I, J, and K. So we can see that I, J, and K can move, they can change with time, they can make a translation or a rotation. So here di over dt is different than 0. Whereas here I1, J1, and K1, these three vectors are fixed. So di1 over dt is equal to 0. Okay, so I1, J1, and K1 don't change with time, whereas I, J and K are changing with time with the moving frame. So we have here an observer at O. Here we have the moving observer. For example, if we take the same example as before, here we have the child. This is the moving observer. Now we have a moving particle. We have a moving particle represented by the point M. It can be the ball which is being thrown upwards. It can go up then down. So here we have our moving particle. Okay, this moving particle can be observed by O1, an observer at rest, and it can be seen by a moving observer at O. So if we take the coordinates of point M with respect to the fixed observer, so M has x1, y1, and z1. X1, y1, and z1 are all dependent of time, because while the moving particle is moving, M will change its coordinates. They are time dependent. We have x1 of t, y1 of t, and z1 of t. So why we have this index 1? Because I'm saying that these coordinates are seen by the fixed observer in the fixed frame. Okay, so observer O1, the position vector is O1m, and this O1m can change with time. So the observer O1 will see the absolute motion of M. Okay, here the absolute motion is seen by an observer at rest, which is the observer at O1. But also, this point M can be observed by another observer in the moving frame. If we take the motion of the ball represented by point M, it can be seen by also the child. The child is moving while the truck was moving. So M can also be seen by an observer in the moving frame. It can have as coordinates x, y, and z. O will see the relative motion of point M. Okay, so the moving frame will see the relative motion. The moving frame will observe or see the relative motion, whereas the fixed frame will see the absolute motion. يعني الحركة المطلقة بيشوفها الأوبزرفر الثابت بمحله، بينما الريلاتيف موشن عم بيشوفها شخص عم يتحرك مع تحرك الموفينج فريم. Okay, we now write O1m as x1 along I1 plus y1 along j1 plus z1 along k1. Why I am using I1, J1, and K1? Because here O1 is the observer. When O1 is the observer, O1 is the origin of the fixed frame that has as unit vectors I1, J1, and K1. That's why I added the index 1 here, and here. OM can be written as xi plus yj plus zk. So when I say OM, it's the observer at O who is observing this motion. So we are talking about the moving frame that has as coordinates that has as unit vectors I, j, and k. So OM is equal to xi plus yj plus zk. This is OM. This is the motion of M as seen by the observer at O, while O1M is the position vector of point M as seen by the observer O1. Let's now take a fixed point in the frame OXYZ, like the point P, that has as coordinates 1, 1, 1. So P is a fixed point in the moving frame. This is a point that is not moving in the moving frame. So therefore, after time delta t, for example, the moving frame will make some type of rotation or translation or anything. It could be here. Okay, it could be like this. And since point P is a fixed point in the frame OXYZ, then P will have the same coordinates 1, 1, 1. So we can see that OP here didn't change. It has the same coordinates. So XYZ for a fixed point in the OXYZ frame keeps its coordinates. But O1P has changed. O1P vector has changed. So what happens? In fact, while the moving frame moves, everything inside this frame will move with this motion. So we can take as an example that OXYZ is the frame associated to the truck, and P, let's say, is the point related to the child. So the child is fixed in the, it has a fixed position in the truck, but as the truck is moving, the child will have the same coordinates as seen by an observer at O, but this child will have changing coordinates as seen by an observer on the ground, for example, at O1. So a fixed point in the second frame, as the point P, for example, with constant coordinates x, y, z, appears to be moving in the first frame and has coordinates x1 t, y1 of t, z1 of t. So point P will appears to be moving with respect to O1. So P will move relative to O1, but P will be constant, will have constant coordinates as seen by an observer at O. The motion thus defined relative to the space of the frame O1, X1, Y1, Z1 is called the driving motion associated with the point considered fixed in the space defined from the frame OXYZ. So to resume, the driving motion is the motion of the moving frame relative to the fixed frame. So here it can be, for example, the motion of the car relative, or of the truck relative to an observer at rest. Now let's see the composition of velocities. We can deduce the velocities based on our position vector. So the equation of motion of point M with respect to the fixed frame is given by the vector O1M equal O1O plus OM. So OM, let's go back to our point M. So O1M can be decomposed as O1O plus OM. And therefore, if we make the derivation of d1 om over dt, we can obtain the absolute velocity. Why is it called an absolute velocity? Because it's seen by an observer at O1, and O1 is the origin of the fixed frame. So dO1m over dt is equal to dO1o over dt plus dOm over dt. And so the first term will give us the velocity of point O. It's the velocity of the moving frame with respect to an observer at rest, plus dom over dt. We said that om can be written as xi plus yj plus zk. So here we have to pay attention. Vectors I, j, and k are moving. I, j, and k are unit vectors in the moving frame, so they are moving. They can rotate, they can translate, so di over dt is different than 0, dj over dt is different than 0, and dk over dt is different than 0. Therefore, when we write the expression of VA, we will obtain V, the velocity of the origin, plus, so we need to make the derivation of xi plus yj plus zk with respect to time. So here we have dxi over dt. We need to write it as in the form of uv prime. So we will obtain two terms for xi, for the derivation of xi. So these two terms will be x dot I plus x di over dt. Similarly, when we make the derivation of dyj over dt, we will obtain two terms, y dot j plus y dj over dt. Similarly for zk, they will give z dot k plus d dk over dt. But I wrote it in this way to assemble all x dot y plus y dot j plus d dot k, because this form is interesting. So we need now to simplify this writing, di over dt. What is it equal to? As we have seen in the cylindrical coordinates, or in polar coordinates, we proved that ter over dt is equal to omega cross er. Similarly, now we can prove that di over dt is equal to omega cross I, and this we can prove this relationship. Okay, but for now we will just use it. It's easy to prove, and therefore we can use, or likewise we can say that dj over dt is also equal to omega cross j, and dk over dt is equal to omega cross k. Then we can obtain va equal vo plus x dot I plus y dot j plus d dot k plus this term, so plus x omega cross I plus plus y omega cross j plus z omega cross k. Okay, now we can take this omega as a common factor. We can take this omega as a common factor and write, so we'll keep all these like this, and we'll take omega as a common factor, so we'll obtain omega cross x I plus y j plus zk. What is it? This one, xi plus yj plus zk. This is equal to the vector om. Therefore, we can finally write that V absolute is equal to Vd plus Vr, where Vr is equal to x dot I plus y dot j plus z dot k, and Vd, finally Vd, the velocity, the driving velocity is it's the velocity of the moving frame. It's equal to Vo plus omega cross om. Okay, this means, so the driving velocity can be seen as the velocity of the moving frame, the velocity of translation of the moving frame, plus the velocity of rotation of the moving frame. So we need to memorize this equation, Va equal Vd plus Vr, where Vd is Vo plus omega cross om. So we have a motion of translation and a motion of rotation it's a combination of these two motions, and Vr is equal to x dot I plus y dot j plus z dot k. We can also deduce the composition of accelerations. It's a bit more complicated, but not difficult. So the absolute acceleration is equal to dva over dt. It's the definition of the acceleration. So we need now to derive the expression of va as a function of time, or with respect to time. So we will use this line. So it will be equal to dvo over dt plus the derivative of these all three with respect to time plus the derivative of omega cross xi plus yj plus zk over dt. So the first term, it's equal to the acceleration of point O. It's the acceleration of the origin, so it's the acceleration of translation of the moving frame. The second term will give us, so as we said that x dot is changing with time, or x is changing with time, and I is also changing with time, so we will have x double dot I plus y double dot j plus z double dot k plus x dot di over dt plus y dot dj over dt plus z dot dk over dt. Again, we will reduce this writing. Di over dt will be equal to omega cross I. So and dj over dt will be equal to omega cross j, and dk over dt will be equal to omega cross k. And finally we'll keep all these as they are, and we'll take again omega as a common factor, so we'll obtain plus omega cross x dot I plus y dot j plus z dot k. And what is x dot I plus y dot j plus z dot k? It's equal to Vr, the relative velocity. And the third term is equal to, so d over dt of omega cross xi plus yj plus zk. So first we will make d omega over dt cross xi plus yj plus zk plus, now we will keep omega cross and make the derivative of xi plus yj plus zk. So we'll have now plus two other big terms. The first big term will be omega cross xi, x dot I plus y dot j plus z dot k plus, this is the second big term, omega cross x di over dt plus y dj over dt plus z dk over dt. And again, di over dt can be written as omega cross I, and dj over dt can be written as omega cross j, and dk over dt can be written as omega cross k. Then we can again take omega as a common factor. And finally we'll have alpha, which is equal to d omega over dt cross om plus omega cross Vr plus omega cross xi plus yj plus zk, which is om. Om is xi plus yj plus zk, and this is the third vector here. If we put all the terms together in the expression of a, the absolute acceleration, it will be equal to, so in 1 we will have a 0, and for 2 we will have x double dot a plus y double dot j plus z double dot k plus omega cross vr. And in the third one, we will have alpha cross om plus omega cross vr plus omega cross om. So we will obtain 1, 2, 3, and we have also 4, 5, and 6. 6 terms added together. So 1, 2, 3, 4, 5, and 6 terms added together. And finally, so here they are shown in a different way. A0, we just rearranged them. So the absolute acceleration is equal to A, the acceleration of the origin of the moving frame, plus alpha cross om, so it corresponds to this term, plus omega cross om. So these terms in red can be considered as the driving acceleration. Okay, as the driving acceleration. In French, we say that this is l'accélération d'entraînement. In English, we say that this is the driving acceleration, so it's AD. And we can see that x double dot I plus y double dot j plus z double dot k is equal to AR, the relative acceleration. And we see that we have an extra term, an additional term that can be identified as the Coriolis acceleration. So you might somewhere else in other references or book see that AE is similar to AD, the driving acceleration. Or sometimes we say that this is the training acceleration or the drift acceleration, which is in French l'accélération d'entraînement. So these are different words meaning the same thing. Okay, so you might see in other books, elsewhere on the internet, the driving acceleration or the training acceleration, or I don't know, and training acceleration, the drift acceleration. So all these terms designate the driving acceleration. And in this color we have the relative acceleration, and finally in blue we have the Coriolis acceleration. So yes, the absolute acceleration is equal to a lot of terms. So if we want to compare the absolute acceleration to the absolute velocity, we won't find this additional term. Okay, so this term appears only in the acceleration expression. What am I saying? I'm saying that the absolute velocity was equal to the driving velocity plus the relative velocity. We didn't have any term, so plus VR, we didn't have in the velocity, the absolute velocity, an expression related to the Coriolis velocity. We don't have a Coriolis velocity, we just have a Coriolis acceleration. In fact, this term appears as a result of the derivation over time of some other terms. Okay, you can go back to see the calculation. So this Coriolis acceleration only appears in the expression of the acceleration. We don't have a similar thing for the velocity, for the absolute velocity. We can have some particular cases to be studied. It's when the motion of the moving frame is a uniform rectilinear translation. So if the moving frame only does a translation, it doesn't do any rotation, and with a constant velocity, then v0 vector will be equal to a constant vector, and a0 will be equal to 0, and then the expression of the absolute acceleration will be reduced a lot. So if we don't have any rotation, di over dt will be equal to 0, because di over dt is equal to omega cross I, and omega is the angular velocity. If we don't have any rotation, then omega, the angular velocity, will be equal to 0. If omega is 0, then alpha is also 0. And since the velocity is constant, then also a0 will be equal to 0. And therefore we can write that the absolute acceleration is only equal to the relative acceleration. Then the acceleration of the moving object is identical in both reference frames. So the acceleration as seen by an observer at rest will be equal to the acceleration as seen by an observer in the moving frame. So the acceleration will be constant. Such a change of reference frame ensures the invariance of the kinematic quantity acceleration and is called a Galilean transformation. So what is a Galilean transformation, or what is a Galilean reference frame? A Galilean reference frame means that we have a frame that is moving with a constant velocity vector. v0 is a constant. In this case, the acceleration will be equal to a constant, so the acceleration will be an invariant quantity. It's a constant, whatever is the reference frame. So the absolute acceleration will be equal to the relative acceleration, and this is equal to the constant acceleration.